So we can go ahead and get started. So today we're going to pick up, obviously, what we started last time, which is in chapter 2. So, I believe we're taping now? Where's the...
Oh, it's over here.
It's over here. Okay. So, it'll be taping the screen, which is the most important part to see. If you'd like access to the tapes, it's $19.95 a month. You can just give me cash. It's fine. I'm going to be giving him his cut afterwards. There's a YouTube channel. If you just send me the link, I'll put it up for everybody. That'll be up for you guys as well. All right. So what did we do last time? Last time, let's see what was left. Well, I guess I did not write it down again. So can somebody tell me where we stopped? Here's an example. And we finished it, or we started?
No, we're on
Step
step 2.
2, good. All right. So, okay. Well, I think that's the end of the problem. We got VEC and got, right, we got the 2 voltages, right? So that's it. That was what we were asking for. Yeah, okay. So, yeah, that's, because you can see here, if you take a look at what I have on the previous notes, right, and, right, there's really just, we had the circuit set up, we applied KVL, and then we came up with the 2 voltages. And the voltages are different because I accidentally miswrote the letters, right? We didn't calculate for VEC, we calculated for like VA or something. Anyway, whatever we calculated for, we got the correct answer. Okay, next topic. So the next topic is voltage divider. Some of you may have already seen this if you, well, all of you should have lab, right? Lab number 1, one of the parts asks you to design a voltage divider. So what is a voltage divider? A voltage divider and I'm going to put the notes up tonight. I was able to scan them finally. I want to make sure I was able to scan them in color because I was writing stuff in red. So I was able to scan them in the middle of the video. So it's a pretty basic circuit, but it's a handy one. What we have is a voltage coming in, which we're going to call V in. And let's say we have a source, DC source, coming in at 12 volts. And you have a component that operates at 5 volts DC. Now there are many better ways to attenuate that voltage than this, but this is the first one we're going to talk about. So a voltage divider is just 2 resistors in series. Okay. And we'll call them R1 and R2. And the voltage across the second resistor we'll call V out. Or you could call it V load or whatever. So, the voltage V out is going to be dependent on the ratio between those 2 resistors. Now, the whole idea of the voltage divider is dependent on the fact that the current flowing in this loop is the same. So what I mean is the current flowing through R1 is the same as R2, is the same as V in, and that means also that we're assuming that this current, which I'll call I out, equals 0. So what this means is that the load is not consuming any current. Now that's not a realistic expectation, right? We know that all loads will consume some current. So what we're going to do is talk about how the load consuming current will affect the expression, and also talk about some rules of thumb that we can try to use to minimize its effect. So anyway, the output here is going to be equal to the input voltage times R2 over R1 plus R2. And what you'll see is that this is an under-constrained problem, meaning that we have lots of possible solutions. Okay. If you're trying to get a ratio of 1/4, you could use 1,000 ohms and 3,000 ohms. You could use 100, 300, 10,000, 30,000, whatever. Generally, we don't want to use very small resistances because, well, it all depends on really what the current rating for your device is going to be. At least in lab, on my notes, I always put you shouldn't be using any resistors that are smaller than 1 kilo. And so so what's good about the voltage divider? Well, first off, it's easy to design and build. But what's bad is that it wastes a lot of energy. Because how does this thing really work is if you're trying to get an attenuation by 1/4 or by 3/4, meaning that 1/4 of the voltage is left over, 3/4 proportionally of that energy is going to be emitted off as, okay, so what you're actually doing is you're heating the R1 resistor and dissipating that energy, and then you're left with 1/4 of it at the power at the output, and so that gives you a 1/4 ratio between the output. So I think that's it for this slide. All right, so transfer function. Worth writing again. Okay. So now what we're going to do is we have that expression, the one right here. Okay. But let's try to derive it. Okay. Let's see if we can, using just the circuit analysis techniques that we've learned so far, which are pretty limited. I mean, it's only what we 3 and 5. Can we derive the input-output relation? So first off, are you guys familiar with the term transfer function? Right, transfer function is simply just a term that refers to the input-output relationship for a component or for a circuit or anything. Normally, it's described in terms of what we call a magnitude and a phase shift, but this is DC, so we don't. So V out, what we're going to say is that V out over, V out over V in is equal to some transfer function, which is in turn dependent on R1 and R2. Okay, those are the two values that determine how the voltage divider will operate. Okay, and so I don't think there's any need to redraw the circuit. Okay, we already have the circuit up here. And for this, what we're going to be doing is we're going to assume no load condition. That means that this I out equals 0. That is definitely the case. And we have all of our values labeled. The only thing that we don't necessarily have labeled is the voltage across R1, and I can give that a name. I'm just going to call it VR1, and that's going to be its polarity, positive and negative. So this is V in, this is VR1. VR2 is the same as V out, and then we have a current I that's going on. All right, so what are we going to do? All right, the first step actually is going to be to make a plan. Make a plan to approach the problem, because we haven't dealt with a lot of these types of problems yet. So we need to think in our head, okay, what's the starting point? That can often be the most difficult thing about this class is you know all these different equations, you know all the different tools that you're given, but when you're presented with something, it's just like, I can just get that first equation, I think I can take it from there. So let's think about this for a second. So you know that you want to define V out, okay? Really, I mean, you could move this over here and say V out as a function of V in. So we want to start out by defining V out, okay, in terms of whatever we can. And I'm going to write whatever. What I mean there is we have several different expressions that we can use that will define V out, and we'll try that. Next, what we're going to do is we're going to try to calculate, or I'll say define, any related values such as current. And when I say related, I mean those that show up in the equation for V out. And then lastly, we're going to make our substitutions, and we're going to try to solve everything down to what we want. So and the reason why I'm going to put an X here is because I want people to take this as one way of doing things, but it's not necessarily the only way. Okay? Some people like to just throw a whole bunch of equations out on the paper, on a piece of paper, and try to sort them out on their own. Some people like to start from the beginning and work to the end. Start by defining V in and then work to V out. So this is really just one way of taking a look at the problem, but it's the one that we're going to use here. Okay, so let's do the first thing that I said. So I'll label these A, B, and C. So step 2 is going to be to define V out. So how many different ways do we have of doing that? Anybody tell me? Now I'm not saying define V out as a number, but just V out as a function of other variables. Right, there's 2 laws that stick out right away that you should be able to use to define V out, right? One would be KVL. And then the other one is KCL? Ohm's law, exactly. Ohm's law. KCL really doesn't help us finding voltages, at least directly. So let's try writing that out for this guy here. So, so we have KVL, a KVL-based expression, and we're going to have an Ohm's law-based expression. So the KVL one, right, is going to say that if we assume this to be the positive polarity, the reference polarity, it's going to say V in minus VR1 minus V out equals 0. Okay? Ohm's law is going to say that I, R2, equals V out. Okay, so we have 2 different options. Now, what we're going to do is, we don't have to choose yet. We'll leave these here. Okay, we're going to move on to step number 3, and then we're going to sort of backtrack and see if we can figure out which one makes the most sense. And so we're going to define related. And when I said related, I said values that show up in the first set of equations. So what are the related values? We see Vn, we see VR1, we see I, and then R2, and that's known. So, all right. So what can we define? I is going to be a little bit difficult to define because really KCL will give us sort of this self-defining relationship. It will simply just say that I equals I in any node, right? Because you can apply KCL here, and you know the I coming in is equal to the I leaving, and then, well, so you're not really getting too much out of it. We could also try Ohm's law. Okay, we've already used Ohm's law up here for V out, but there's another one that we could use for VR2 or VR1. So we know that VR1 is equal to I times R1. We also have KVL, which would allow us to put things in terms of VR1, but it's going to be redundant. Right? Because all I'm going to end up with is another expression with these 3 terms in it. So it looks like these expressions right here, these are the ones that we have to deploy. So let's decide which one of these are useful and how we can combine them. Our goal, right, is to take pieces from over here and move them up here. Right? We want to, in the end, have an expression that's in terms of V out. So we're not trying to substitute this way, we're trying to substitute it the other way. So what different combinations? Now this is where, for better or for worse, you have to start trying to imagine what different combinations are. So what would make the most sense here? We want to end up with the same number of expressions as we have in unknowns, or ideally, one expression with one unknown. So I'm going to give you guys a second because I want you to think about this. Yeah.
We have expressions for both VR1 and V out.
Mm-hmm.
We have IR1, IR2, and I is the same for both those, so we could put those in the first KVL equation.
Mm-hmm.
Kind of combining those equations, actually.
Yeah, most definitely. So which one of these expressions were you talking about? Yeah. This one?
The own one, yeah.
The own one. So you're talking about sticking this one up here.
Yeah.
Okay, that makes sense to me. Let's do that. All right, so that goes right there. So that'll give us an expression which is now in terms, so how many unknowns will we have? We'll have V in is not really an unknown because that's going to be, our output is going to be V out over V in. So we'll have I1, R1, V out, so I will be still unknown. Now, how could we get I to be known? Using this expression right here, right? Because we know V out, we know R2. So we can do that, and we'd end up with an expression that would only be left with the variables that we're concerned with. So I think that'll become a little more clear once we do the substitution. Okay, so let's start off with step number 1, which is going to be the one that you suggested. So I'm going to say this is step 1. And then this will be number 2. All right, so step number 1, we're going to have, and I'm going to put V out on the left-hand side. So we'll have V out will be equal to V in minus, and now instead of VR1, we're going to have IR1. Okay? Now, if we wanted to, we could go ahead and get this into the right form straight off the bat, right? We could divide both sides by V in, and that would give us V out over V in on the left-hand side. So let's go ahead and do that. So I'm going to divide this by V in. I'm going to divide this by V in. So what we have is this is our desired final result, and what we'll have is 1 minus I R1 over V. Okay, now let's make our second substitution, which is going to be this into I. So that means that we'll have V out over V in equals 1 minus, and what's the exact form we're going to use? We have to switch this around a little bit, right? We have to switch this to essentially V out over R2, right? Because I is equal to V out over R2. And so what that'll leave us with is V out over V in, R1 over R2, both of those, right, multiplied together. And so what we can do is we can pull this over to the other side. So what we'll have is V out over V in times 1 plus R1 over R2 equals 1. Right? Because this has a V out over V in term in it. So we can pull that over and combine it with this one over here. And then now we want to simply just take this coefficient and move it over to the other side. But before we do that, this is going to be tough to invert right here because it's two different terms. If we combine them and make it a single fraction, it'll be easier to invert. So in order to do that, what we'll do is we'll just multiply this by R2 over R2. And so what we'll end up with is V out over V in times R1 plus R2 over R2 equals 1. And then, I don't think I need to go to the next sheet. Hopefully you can see what that is going to give us when we flip it. Is going to be V out over V in equals R2 over R1 plus R2. And that's our final. So, I mean, I'm going to be honest with you. That was a really long and really convoluted way of doing it. I mean, I think that most of you, in your mind, could probably do it without having to write out every single step of the process. But if you break it down to its most basic elements, that's sort of the process. You can combine together equations that are KVL, KCL, Ohm's law, and as long as you're aware of what the end result is, which is getting something that is in terms of V out over V in, for any problem that I would give you, at least you'd be able to. So this matches what we got on the I don't think that you necessarily have to memorize something like this. I'm not going to ask you on quiz derive the transfer function for a voltage. What I might do is I might ask you to give me the transfer function for a different type of circuit. And so those general skills, the ability to combine those equations together will come in handy, but it's not like repeating this one. Okay, so now, the next question is, how does a load affect operation? Because so far, we've been operating with the assumption that there's no load there, so let me quickly draw another voltage divider. Okay. And so our V out is still over here. The only difference now is that we have this guy. And this will represent the device that's actually consuming power from the user. And so the first step in analyzing this would be to now we haven't learned this expression explicitly yet, but I can go ahead and just give it to you now and then we'll review it later. It has to do with how we combine resistors together in circuits. So there are very good, easy to use rules that allow us to combine resistors that are in series and in parallel. So I'm going to put them in this box. I'm going to put them in this box right here. We have a resistor 1 and a resistor 2. okay, R1 and R2. The combination of the two is R1 plus R2. Okay, that's a series combination. If we have two resistors that are in parallel, then the equivalent is R1, R2 over R1 plus R2. And that's called a parallel.
Does that come from the 1 over R equivalent equals 1 over R1 plus 1 over R2?
Exactly, yes,
Okay.
that's another form of that.
Okay.
This is the form for only two. If you have multiple, okay, the more general equation is that 1 over R equivalent is equal to the sum from K equals 1 to whatever the number of resistors are of 1 over RK.
Okay.
So this expression is easier to use if you only have two. If you have K or whatever more, then this expression. So essentially what this says is that although the resistances don't sum when they're in parallel, the conductance. And so what, I don't think we've said this explicitly, what does it mean to be in series, right? For two resistors to be in series, they have to share a common connection point and have nothing else connected to that point, okay? So series means two elements only are adjacent to their common node. Okay? If there's a third thing shooting off here, they're no longer in series. For parallel, there can be other things over here. For parallel means that they share the same end nodes. And there may be others that doesn't have any effect. You can combine two. There could be other nodes. All right. So so what case do we have up here between R2 and RL? They're in parallel, right? Because they share the positive and negative terminals of the Vout voltage as their nodes. And so if we wanted to come up with an R equivalent, which we could say is R1 in parallel with R2. That sign right there means parallel. Then simply that's R1 or L, sorry, not 2. R2 and RL, I apologize. So R2 and RL over R2 plus R. Okay. So what's the difference going to be? Is that now and let me just do this on the next page. So let's compare the way that the transfer function for the voltage divider both with and without the load. So without the load, we already know what that would look like. V out over V in equals R2 with the load, V out over V in would be equal to, right? So now, when we combine these two together, it looks like another voltage divider, right? With R1 and R2 being replaced by the equivalent combination of those two together. Does that make sense to everybody? Right, this is a voltage divider. Good old voltage divider that we're used to seeing. This is a voltage divider where now our secondary resistor is the parallel combination of these two together. So all we're going to do is just write that out. So I'm going to replace R2 with R equivalent. R equivalent. R, E, Q. R1 plus R, Q. We could also say that's equal to R2, RL, R1 plus R2, R. Parallel combos of those together. So, and I can write this out and put the full form in there, right? Because this is really I can put that in my notes. So that's the difference. Okay, this is what the output and input voltage ratio is going to be when we don't have a load, and this is what the output and input voltage ratio is going to be when we do have a load. So you can see that there is a difference. I don't think these two expressions necessarily tell us, I mean, not from eyeballing, which direction it's going to go in. But let's take a look at the more interesting question, which is when can we ignore RL? Because our goal is to come up with a rule. One that says we can use this expression right here, even when we have a load, as long as the load is something. All right? And we're going to set a requirement or a threshold for that. So step 3 is to formulate an assumption for RL that allows us and so this one up here is what we call the ideal. All right, because in the ideal case we don't have it. Okay. So now, let's take a look back at the parallel combo. What's the parallel combination of a 2 ohm and a 2 ohm? So we have 2 times 2 over 4.
1.
Yeah, right. So 1. When you combine 2 resistors with the same value, you end up with half of them. Parallel combinations of resistances always make the resistance go down. So whatever the lower resistance is of the two, no matter what you combine it with, you're always going to end up with, at best case or highest, that lower resistance and lower. It's never, a parallel resistance is never going to make that equivalent resistance go up. Okay, what happens when we have a parallel combination between a resistor and a short circuit? We already talked about that one, right? So if we have, this is 10 ohms and this is 0 ohms, the parallel combination is going to end up giving us 0, right? Because that's what a short circuit is. And then let's talk about the other case. What if we have R1 in parallel with an open circuit, where the resistance is infinite? Right? The parallel combination is simply going to be equal to the R1. Yeah. So what we know is that the larger the second value is, the less effect it's going to have on the parallel combo. Right? Very small resistances, which is the short circuit, has the ultimate effect of completely changing the resistance, and very large values have the effect of the lesser. So we know that to a certain point, right, this is going to have to be an assumption which says that RL is bigger than a certain value. Because to get this to match this over here, right, there's going to be a certain threshold for RL. Once RL drops below that value, then we're going to have to use this expression. But if it's above that value, with the ultimate case being an open circuit, we can probably use this over here. So, so let's just use this expression for a second. Well, I've kind of already explained it. The rule is this, essentially. I'm just going to stick to it. And this is a rule of thumb we're going to use in this class. Depending on what the application is, you could use a different rule of thumb. Normally what we're going to say is that we want RL to be at least 2 magnitudes order larger than R2 in order to assume that the combo of R2 and RL is equal to R, or approximately equal to R2. So to give an example of that, let's say we had a voltage Vn, we had an R1, we had an R2, and so this is going to be 100 ohms, this is going to be also 100 ohms, and this right here, the load, is going to be 10,000 ohms. And so if we calculate the parallel combo of R2 and RL, that's going to be 10,000 times 100 over 10,000 plus 100. And so let me see what the exact value of that is. Okay, and so you can see here that we're ending up with that when we follow our rule, which is right here, we can see that the parallel combo of these guys is approximately equal to R2. And then, in that case, V out over V in is equal to R equivalent over R1 plus R equivalent is approximately equal to R2 over R1 plus R2. And anyway, so we end up back together. So when you're building voltage dividers in lab, I usually say that you can't use any resistor that's smaller than 1,000. So that means that your loads are going to have to be pretty big. So if this right here were 1,000, that means that the smallest load that you could use would be what, 1,000 at this point, larger than this. Now, is this close enough to 100 to warrant you saying they're approximately equal? When it comes to stuff like this, it really matters on what your application is. And I always use like the toaster versus like the spaceship example. If you're building a toaster, most times 99 is close enough to 100 to just be 100. If you're building some piece of like medical equipment or your spaceship, right, something where human lives are dependent on it, you're probably going to want to up this to 3 orders or 4 orders of magnitude in order to be satisfied. So this rule is one we're going to use for the class, but you have to, depending on your application, adjust how you design it. All right, any questions on voltage divider? So the next thing I have written in here is how to design a voltage divider. So I'm just going to put this up on the screen and talk through it because I think we spent a lot of time going over this idea. Okay, so how to design a voltage divider. I gave you this case where we want to end up with 3 volts at the output, and we have 10 volts at the input, and we don't know what the R1 and R2 resistors are, but we know that the load is 1 kilo ohms. Okay? So you know that that designing a voltage divider is an under-constrained problem, which means there's multiple solutions that can work. Right? You can start with R1 and calculate R2, or you can start with R2 and you can calculate R1. So the first thing that we have to worry about is the whole relationship between R2 and RL problem. So the first thing we're going to say is that our R2 value had better be 2 orders of magnitude smaller than 1,000. And so that means that the maximum value, and this wouldn't work in our lab because I tell you not to use these small resistors, but for this example, we'll say it's okay. So you know that R2 at maximum has got to be 10 ohms. Then what you can do is work backwards using this expression. Because now that we've essentially satisfied our assumption, we can use this. We can use R2 in place of R equivalent. And then we plug in a value of I don't know why I put 100. I don't know why I put 100K right there. The value is 10 ohms. We put in a value of 10 ohms. We use 3/10 as our ratio because, right, we want to end up with 3 over 10. And then you can go back and solve for R1, which gives you 23.3 ohms. That makes sense to everybody? For designing a voltage divider? Start off with, obviously, what your desired ratio is. Then move on to consideration of what your load is in terms of the resistance range. And then you move backwards into figuring out what R2 is, and then you can calculate R1. Okay. So next thing, and I know that this came up a little bit in chapter 1, which is weird because they didn't really discuss it in the book. But what's a dependent source? So we talked about independent sources. We didn't really talk about what dependent sources are. So what? What's a dependent source? So a dependent source is one which is dependent on another value. The most basic description for a voltage dependent voltage source looks like this. We have a little mini circuit over here. Then we have an electrically disconnected second circuit over here. Okay, so this is V out, I'm going to call it. I'm actually going to say this resistance is equal to 0, so we can ignore that. This right here I'll define at the end. And this I'm going to call V1. The resistance R1 is not really important. And so it's 5 volts applied right here. And to stay consistent with my other notes, I'm going to call this V2. So normally what you're going to see is that a dependent source will simply be defined by some expression that looks like this. Okay, 3 or at some constant times of another voltage in the system, potentially another current in the system. And so when you solve these types of circuits, every time you need to know this value over here, you have to refer back to V1. So what is this voltage going to be in this example? Right, 15 volts. This is 5 volts. Same thing as V1. This voltage is 3 times V1, and so we end up with 15 volts. Okay, there are 4 different types of sources, of dependent sources, that we have to worry about. Okay, there are voltage-dependent voltage sources, voltage-dependent current sources, and then the opposite. Current-dependent current sources and current-dependent sources. So you could have something that looks like this, and it could be 3 times Vx. You could have something that looks like this, and it could be 3 times Ix. You could have something that looks like this, and it could be 3 times Vx. Or you could have something that looks like this, and it could be dependent on 3 times. Where Ix and Vx are just generic other voltages or currents that are in the system. In either case, it doesn't matter what they're dependent on. There's always going to be, this is going to be Vs, okay, the voltage is defined there, and Is, okay. So even up here, when you're multiplying 3 times V, the output is current, okay, in amps. And so we give these names. We call this generally voltage-controlled voltage source. We call this voltage-controlled current source. We call this current-controlled voltage source. And we call this current-controlled current source. So if you see those 4-letter acronyms, that's normally what they refer to. VCVS, VCCS, etc. I'll give you a second. Now the concept of dependent sources, I don't think is one that's very difficult to comprehend. Everybody's like, okay, yeah, this was dependent on something else. Where it becomes more difficult is when you start solving circuits that have these. Because now when you write out your KVL and you have a circuit with dependent voltage, you got to put a dependent voltage in your KVL. And then that just leads to a whole. But we'll get to that. Now, moving on to another topic. So, we talked about how we could combine resistors together, right? We could combine resistors together into series and to parallel combinations. Can we do the same thing for sources? And the answer is yes, we can. And there's different rules on how we can do that. So, let's say we have a system or a circuit that looks like this. Okay, so this is V1, this is V2, this is V3, this is V4, this is V5, R1, okay. So, the question we ask ourselves here is, can we simplify this network? And the reason why simplifying is good is because it makes it easier to solve. Right? The fewer components that we have to deal with, the smaller our equations will be, and right, the easier it will be to solve. So what are the rules here? Let's start off with another question. How could we solve this type of situation? We could do something like what we did for the voltage divider, right? Put together some combination of Telegin's theorem, KVL and KCL, and Ohm's law. All right, we could use some combination of those together. But there's a couple caveats. Really, this is just another form of KVL. Right, for our purposes at least. Right, we used Telegin's theorem to derive KVL, so I mean it's going to be a little repetitive in terms of use. Is Ohm's law going to help? Probably yes, right? That will help us to solve this. KVL will most definitely be useful. And is KCL going to be useful for a circuit like this? Not really, because normally, right? Well, not normally. It is just one single rule. So the only expression that KCL would give us is that the I, if you wanted to, you could define individual currents for R1, V2, V3, etc., and that KCL would tell you that they're all the same. So KCL, not so much. All right, so let's try to solve this thing. We'll solve it using the approaches or the methods that we're used to using. And then we can go back and see if there's some sort of a pattern that arises, something that would have allowed us from the beginning to combine these things together. When we already learned one way to combine things together, we know how to combine the resistors, right? Okay, we know that resistors that are in series can be summed together. Now, these two resistors are not really in series. They're not, okay? The trick is, though, that if we're trying to solve for the current flowing through this loop, we can shift the order of things around however we want. And that'll become evident when we write out our KVL. So we can move these two guys to be in series. But I don't want to skip ahead too much. When we write out the KVL, that'll become evident. So step one is to write out KVL for this. And so I'm going to need the circuit sort of on the screen to see that. What I'm going to do is I'm going to ask one of you guys to give me the KVL for this one. And let's assume that V1 is the reference direction. We haven't done one of the things which I said from the beginning, which is to try to label all of your voltages and currents in the circuit, because that'll make it easier for us to write. So what's KVL for this one? I'm hoping by now people can rattle this off.
Should I do were they all after zero, or like what do you want to
Yeah, just do it, they all have to zero.
Okay, so V1 plus V2 minus V3.
So let's go with the assumption right now that we're going to go in order. So I know we can shift things around, but let's just go around the circle. So we'll include VR1 next.
Oh, sorry. Okay, so V1 plus VR1, or?
So the easiest way to think about it is imagine you're following the current and the order that you see the term. So this goes minus plus, plus minus, plus minus. So anytime you see plus minus, yeah. So V1
minus VR1 minus V2 plus V3 minus V4
well, don't forget that.
minus VR2 minus V4 plus
Great. Okay, so that's writing out KVL. And already you can see already you can see right from writing out KVL that the order of these terms doesn't matter. We could have easily taken the approach that he was saying and gone through all the sources first and said V1 minus V2 plus V3 minus V4 plus V5 and then gone back and did the others. It would have given us the same thing. So that's what my final stuff was. So what does that tell us then? It tells us that So we can group terms as we wish. And one way that might make sense to do that is we can group the sources together and group the resistors together. So what we'll end up with is V1 minus V2 plus V3 minus V4 plus V5. All right? And then we'll be left over with a minus VR1 plus VR2 equals 0. Okay? And so now what we have is all of our sources and all of our resistors. So what's stopping us from simply just defining a new term? Finding a new term, right? We could say, we could rewrite this, the KVL, and simply just say Vs minus, and now there's a little bit of, we can play around with this right here because we know what is VR1. If we substitute in Ohm's law, what is VR1? IR1. And then right, you can combine the i's together. And so we end up with an expression that looks like this down here. So what we've done is we've replaced the resistors, two series resistors, by their equivalent. And we've also combined all the sources into one. And so, right, we could redraw this circuit up here in a much simpler form, one that looked simply like this. Okay. Now, we gain a lot, but we lose some when we represent the circuit. What we gain is it makes it a lot easier to solve. Now, it was probably easy to solve to begin with, but again, we're trying to illustrate the idea. But we do lose what we call resolution. So with this circuit up here, if I wanted to know what the voltage between, I'll just call this point A or node A and node B was, I could calculate that, right? VR1 plus V2. Those nodes are gone now here below. So this simplification, okay, results in loss of resolution. With regard to nodes. It makes it easier to solve for I, but it makes it harder to solve for other. So when you use this, it depends on what your end goal is. But the good thing is that once you solve for I, going back to the previous figure, it makes it much easier to solve for VR1. So it could be different steps of multiplication.
In the beginning, did we say that the R1 and R2 were in series?
Well, so the thing is, again, the way that they're drawn right here, they are not in series.
Okay.
When we have a single loop, we can reorder things
Right.
and make them in series. Now, let me give you the example of when this doesn't work. You have a circuit that looks like this. Okay, now all of a sudden, you can't reorder it in pattern one. Okay? You cannot, although you can combine these two together.
Because they're in the same loop.
They're in the same loop and there's no other parallel paths. You cannot okay, you cannot combine those two together. Now we'll learn ways to deal with circuits like this, where, because we've talked about combining things together in series, there's also ways to combine things together in parallel. We've already talked about combining resistors together. Sources, the rules are a little bit different. So one of the ways that we're going to solve circuits in this in chapter 2 is we're going to essentially treat circuits like an accordion. Okay. Well, what we're going to do is try to push that outer box. Okay. Make all of these, push them together into a single branch, and then you have a single loop. Okay. And so we might have even bigger ones with more boxes moving outward. And so what we would do is simplification, simplification, simplification in order to get solved for the current through that one loop. And then fortunately, when you want to get, let's say, the voltage across this resistor, then you have to do expansion, expansion, expansion. But at least you're starting with a value that's known. So you solve for that. Okay, so the next thing here is example 2.15, which I don't think we'll have time to finish. So we'll stop there. A couple things, though, before we go on. The quiz, right? I'm going to try doing an online quiz for this class. So Thursday, it's gonna be in the evening because I figured that during the day you guys will have classes. I'm not going to give time during this class to do it. So 6 o'clock, or actually I think it says 5 o'clock till midnight. The quiz will be open. You'll have 45 minutes to complete it. Please do it by yourself. You can use any materials that you want. Have your book, whatever in front of you. That's completely fine. You don't get a second try at it or anything like that, or something. The quiz is done like that. And yeah, so just don't forget, and don't start the quiz until you're really ready to sit down and spend the time. If you do have a technical problem, keep your phone near you, take a picture, or preferably a video of what happened. Okay, that way it helps me not have to deal with IT saying there was not a problem, you saying there was a problem, then having to work with it. So just make it easy. For some reason, even if it's your internet connection or whatever happens, if there's a problem, it's only on chapter 1. And I haven't had any questions on homeworks yet, so, yeah. Yeah, actually, I will be collecting the homework again, so I'll put